You got it? Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. I just pray that you'd bless this class, help us to glorify you, Lord, in what we do this day, Lord. In your name I pray. Amen. All right, so let me just briefly review a little bit what we did last time. So we talked about what are inverse sine, inverse cosine, inverse tangent. I would remind you that they are local inverse, right? So, in fact, inverse sine of x only gives you back x when x is between minus pi over 2 and plus pi over 2. For cosine inverse of cosine of x only gives you back x when x is from 0 to pi. That's where it is the inverse for the cosine function. For tangent, the inverse tangent gives you back an angle. Inverse tangent of x gives us back x only when x is between plus and minus pi over 2, not included. All right, these are the definitions. Last time we derived, what did we do? We calculated the derivative of this. We showed that d dx of, inverse sine of x is 1 over the square root of 1 minus x squared. And we also showed that d dx of inverse tangent of x was 1 over 1 plus x squared. Those we worked out. Okay. Now, one of your homework problems, is kind of like this discussion over here. An example I should probably add is this one. Now, what's not given in the homework problem is this, right? So it's like, let me just erase. Start again. So here's what's given, something like this. They give you a little triangle. They tell you that the angle is inverse sine of x. And they ask you to derive various other trigonometric quantities from this. It's actually a very easy problem once you understand the idea of it. It's important, too, because we use these little triangles for trigonometric substitution next week. Now, so if the opposite side is x and the hypotenuse is 1, that means sine of theta, right, is x over 1, which means the inverse sine of x is theta. So this is all, it's labeled consistently, right, to start with. They didn't set us up to fail. It's a reasonable triangle. It's logical in terms of the relation between sine, the opposite side, and the hypotenuse. And then, what's the adjacent side have to be? Right, the square root of 1 minus x squared by the Pythagorean theorem. Because this squared plus that squared has to give us back 1. Okay? Now, once I've written that, it's a breeze to write down what's like cosine theta, what's tangent theta, what's cotangent theta, what's, secant theta, etc. Cosecant theta, while I'm at it, fine. Cosine theta is what? It is the square root of 1 minus x squared divided by 1, right? Yeah, I won't write the divided by 1 if that's okay with you guys. Tangent theta, opposite over adjacent, x over square root of 1 minus x squared, right? Cotangent is what? Flip it over, right? 1 minus x squared, all divided by x. Secant theta, I shouldn't write over here. Secant theta, 1 over the square root of 1 minus x squared. And let's see here, what do we got? Cosecant theta, that's 1 over sine theta, right? So that's 1 over, what is sine theta? It's x, right? You're like, but the problem doesn't ask me about theta, it asks me about things of inverse sine. Well, theta is inverse sine, right? So this is the cosine of the inverse sine of x, right? This is the tangent of the inverse sine of x. This is the cotangent of the inverse sine of x. This is, why did I sign up for all this? Secant of the inverse sine of x. And this is the cosecant of the inverse sine of x. Now, this is important to know because we don't like to write answers that have inverse trigonometric functions in them if we can get away with it. Like, we much prefer algebraic expressions. What's an algebraic expression? It's an expression built from trigonometry. No, an algebraic expression is an expression built from algebra, right? A finite sequences of additions, multiplications, subtractions, divisions, and roots, right? An algebraic expression. And these, in the middle, are all algebraic functions, right? And that's the neat thing about that problem. Yep.
If you understand the form of problem, is the first step necessary? Like setting arc sine of x equal to theta?
No, I put theta there so people could understand what I'm doing better. There are some of you who could understand it without writing theta. Yes. That's fine. It's fine. Now, I'm going to come back to this. I just want to leave that written. So further, so that there you go. Now, there's a few definitions I have left to give you. Definition: the inverse secant of x is defined to be inverse cosine of 1 over x. The inverse cosecant of x is defined to be what? Yeah. Inverse cotangent is defined in the same way we define cotangent. So like cotangent, I think cotangent looks almost the same. It's just like, what does it do? It looks kind of the same as this. It's just like, if I remember right, I forget. And so inverse cotangent has essentially it's kind of like a reflection of tangent, and through essentially the same calculation as we did last time, you can prove that the derivative with respect to x of inverse cotangent of x is what? Minus 1 over 1 plus x squared, right? You could derive that the same way we derived the formula yesterday. So I won't go into that. These two, on the other hand, how do you calculate the derivative of inverse secant now that we have a definition for it? Right? I guess I should be, what x is this defined for? So I'm in section 7.7 of your book, and these definitions are given for absolute value of x greater than 1. What is this in terms of interval notation? Yeah?
I guess, two lines start at 1 and -1 and head in the opposite directions.
So are you thinking graphically? So here's the absolute value function, right? And we're looking for x such that x is greater than 1, right? So above that line, so you got this piece and that piece. In other words, it's minus infinity to minus 1 unioned with 1 to infinity. It's got two disconnected pieces. It's kind of a weird domain, but there it is, right? Nature of the beast. Now, in the exercises, you're actually asked to prove that indeed, here's a claim that these are good definitions. What would make this a good definition is that secant of secant inverse is what? I should hope that this is equal to x again, right? Mm-hmm. And I would also hope that the secant inverse of the secant of x is equal to x. Now this won't be the same x, but what's the domain of secant? What is secant? Secant's 1 over cosine, right? So this is, x is not equal to plus or minus pi over 2, plus or minus 3 pi over 2, and so forth. All right. anyway, that's a claim that you can try to work out. I'm not going to do that today because we're a little bit short on time, and I have this sneaking suspicion we're going to lose Friday. So I must go on if there's going to be time, like tomorrow, for some proper homework questions. So I'm going to go on and not prove this. What's that?
Because of these now.
Yeah, I would be shocked if we don't cancel class Friday. I'm pretty sure. I've been here a little while. Okay, so man, I really want to prove that claim. I must resist. I must resist. I must resist. What does matter, what I should show you, is how to find the derivative of inverse secant, for example. Tell you what, I'll do the cosecant. All right. So that's not a hard thing because, I mean, well, it's hard as, I suppose easy, hard, that kind of depends on where you are. I mean, certain things are hard for all of us. Other things are hard for some of us. And it kind of depends on your background and other things. What I mean is it doesn't require methods we don't already know to do this derivative. We just need to do the chain rule on the derivative we worked out last time. So this is like inverse sine of, let's say, u. So I do what? I do 1 over the square root of 1 minus 1 over x quantity squared times d dx of 1 over x. That's the chain rule. And I'm using what we derived last time, namely this thing, right? The inverse sine derivative with x replaced with 1 over x. So I got to do chain rule. So what I have then here is 1 over the square root of 1 minus 1 over x squared times minus 1 over x squared. All right, so then what? I've got minus 1. Just going to basically write it again. I'm going to put the x squared in the front. X squared. I'm going to make that into an absolute value of x squared. Why can't I do that? Right. Remember, the absolute value of x is defined to be the square root of x squared, right? So the absolute value of x quantity squared is x squared. This is the definition of absolute value. So if you square the definition, I mean, we can quibble over what's the actual definition of absolute value, but we should all agree that if you take the absolute value of x and you square it, you get x squared, because you either got plus x or minus x. So the plus squares to plus and the minus squares to plus. Either way, we get x squared. Agree? All right. So I can rewrite this as minus 1 over absolute value of x times absolute value of x times the square root of 1 minus 1 over x squared. Now the reason I'm doing that is because I want to remind you a little identity that says if I have the absolute value of a, for example, and I times the square root of stuff, then that's the square root of, absolute value of a squared times stuff. Now you're like, well, in fact, by what you just said, that's just a squared times stuff, and that's true, yeah. Now, so applying that right here, we have the absolute value of x times the square root of what? X squared times 1 minus 1 over x squared. I just brought one of the absolute values inside the square root. When I bring the absolute value of x inside the square root, it squares it. And I'm bringing inside something positive, so I'm not like losing a minus sign or something. You have to be careful when we bring things inside or outside square roots. But then there you have it, minus 1 over absolute value of x times the square root of x squared minus 1. And that, my friends, is the derivative of inverse cosecant. Es bueno? All right. See, okay. Another claim I can make today is that if you add inverse sine of x plus inverse cosine of x, and if you add inverse tangent of x plus inverse cotangent of x, and if you add inverse secant of x plus inverse cosecant of x, it's very boring. All of these things add to the same thing. In particular, pi over 2. So this one, you can see page 384. The book shows you why that's true. I might come back to why that's true another day. I know better than to try today. But the other two are homework problems. So not ones that I've assigned you, I think, but to show that these are true. I'm probably going to post some little video about why they're true. I need to think about it some more myself. So anyway, if you'll accept this claim, what does it say about the derivatives of like inverse sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, inverse cosecant? How are the derivatives of these inverse functions related, given these three equations? We've already seen one. Derivative of tangent and derivative of cotangent. Well, the sum of their derivatives is 0, right? But these are minus each other, right? They're negatives. You multiply one to get the other, you get to multiply by minus 1. So like the derivative of, I haven't worked this one out yet, but if you believe that claim, it's immediately true that d dx of inverse cosine of x is minus 1 over the square root of 1 minus x squared. And I mean, come on, let's just think more geometrically for a second. That totally makes sense. It's the same shape as sine, run the opposite direction, right? And this formula is even with respect, I mean, anyway, it makes sense that it should just be the same but minus if you it does, it's intuitively natural, that formula. I know it has to be negative because cosine is decreasing. But by the way, something, I'm not so foolish as to try to graph these today. Now you can tell me what's the derivative, this is, by the way, equal to what? Minus the derivative with respect to x of what? Of secant inverse of x, right? So there you have it. Those are the derivatives of your inverse trig functions. And to each one of these derivatives, of course, we have a corresponding integral, right? For example, if I was to ask to integrate dx over the absolute value of x times the square root of x squared minus 1, I would just say, aha, that is exactly inverse secant of x plus a constant, right? Now that's a quote-unquote elementary integral, since we know this derivative. One of the bigger themes in the next few weeks is this idea. What is integration? It's anti-differentiation, but I would say in terms of a process, what it really is a system of educated guessing. Differentiation, we derive. We actually work out from the definition, base principles. This is the derivative of the power functions, the derivative of the exponential, the sine, the cosine, all this stuff. We can, from the limiting process, derive those things. And then we prove product rule and chain rule and all these things. And when you differentiate something, you just systematically apply these things in order, right? Integration, on the other hand, is a totally different mental process. It's really an organized system of educated guessing, which is what makes it so much harder. But anyway, we're not quite there yet. We still have this background to go over. So, all right. Yes, so this brings us to hyperbolic functions and such. Now, before I do that, though, I just want to give you a couple words about trigonometric identities. We don't need these right away, but we'll need these soon, so we might as well just do it and get it on the table. What are the important trigonometric identities that you should know? I think I can erase these things over here, and I can make a collection of trigonometric identities that we all know. First thing you can write in your notes is cosine squared plus sine squared is what? How about an identity involving tangent? Tangent squared plus 1 equals secant squared. How about cotangent? Let's see here. So when you divide this by cosine squared, we get tangent squared theta. Excuse me. I'm an idiot. Divide by cosine squared. I get 1 plus tangent squared is 1 over cosine squared theta, but that's secant squared theta. And then if I divide this by sine squared, I get cotangent squared theta plus 1 equals cosecant squared theta. So both of these, divide by cosine squared theta, divide by sine squared theta, right? So basically, if you know the definitions of cosecant and cotangent and such, and you know the Pythagorean identity, you automatically get those second two for free, right? This we should know. I suppose we should also know the definitions, right? Tangent theta is sine theta over cosine theta. Secant theta, 1 over cosine theta. Cosecant theta, 1 over sine theta. All right, these things we know. The next level of inquiry, which involves a considerably deeper idea of trigonometry, are the so-called adding angles formulas. So, adding angles formulas. How about this? Cosine theta plus beta is equal to cosine theta, cosine beta, minus sine theta, sine beta. Now, I guess something I should have told you at the start, even, what are very important fundamental properties of cosine and sine is that they're what? Cosine of minus theta is what? Sine of minus theta is what?
Cosine's an even function, right?
Right. So cosine being an even function means I put cosine theta here. Sine being odd means I can pull out the minus. Right. So like cosines eat sines and sines spit them out. There you go. Hate this minus sign. Can't stand it. Sorry. I'll try to be more couth in the rest of my lecture. What happens if you then put a minus here? Right. How about the first, this minus changes to a plus, right? Because I get cosine theta, cosine minus beta, but cosine minus beta is just cosine beta again. On the other hand, the sine minus beta spits out, and minus minus give me plus. So in short, I can just write this. It's pretty nice. Pretty nice. All right, and let's see here. What about the corresponding identity for sine? Sine of theta plus beta. Sine theta cosine beta plus sine beta cosine theta. What happens this time if I put in a minus? I sometimes make calculus 1 derive these. They're not entirely trivial, but they're really essentially equivalent to the law of cosines for what it's worth. So I get plus minus, plus minus. The minus comes because sine of minus beta is minus sine of beta. But anyway. Anybody here know the adding angles formulas for tangent? How would you derive the adding angle formula for tangent? Yeah, we do sine theta plus beta over cosine theta plus beta. So, I mean, there it is. Sine theta cos beta plus sine beta sine theta. I'm sorry, there's cosines in there. Second one, cosine theta, yeah. So sine, cosine, and then in the bottom it's cosine theta, cosine beta, minus sine theta, sine beta. Now if you take this, right, and you divide the top and the bottom by what? So what I'm doing is I'm dividing the numerator and the denominator by the product of cosine theta and cosine beta. If I'm doing this, I better know something about theta and beta. I better know that they're not plus or minus pi over 2, plus or minus 3 pi over 2, and so forth, because if either one of them were that, the product of cosine theta and cosine beta would be 0, and I would be ill-advised to divide by that, right? Like, don't divide by 0. It's still not a good thing. It wasn't a good thing in calculus. It wasn't a good thing in in elementary school. It wasn't a good thing in algebra. It wasn't a good thing in calculus 1. It's still not a good thing. No dividing by 0. It is forbidden. Okay? Yeah. I'm dividing this expression, top and bottom, by the product of cosine theta, cosine beta. So cosine theta, cosine beta, divided by cosine theta, cosine beta, 1. So since I'm dividing by the cosine theta, cosine beta, cosine beta, cosine theta, cosine beta, cosine theta, cosine beta, cosine theta, cosine beta, divided by cosine theta, cosine beta, 1. Yeah, I know. Es bueno? Say si, senor. All right, so there we go. These cancel, and you're left with tangent theta. You're right. It is a plus. As you can see, still something left in the marker. There it is. All right. So tangent theta plus tangent beta divided by 1 minus product of tangent theta and tangent beta. There you go. That's the adding angles formula for tangent. Of course, if you know the adding angles formula for sine and cosine, you can derive it with about 2 minutes of algebra. Right? There it is. What other trigonometric identities are known? Close cousins to what I've shown you. Yeah, the double angle formulas, those we use a fair amount. Oh, stupid. Let's see here. So, for example, if I take cosine of theta plus theta, I get what? Cosine squared theta minus sine squared theta. See what I did there? I put theta equal to beta to get this. But what's that get me? Right, sine squared theta is 1 minus cosine squared theta by the Pythagorean identity. And so what do I have? I have twice cosine squared theta minus 1. So I can solve for cosine squared theta. What do I get? Algebra. Now, think about this. We know sine squared plus cosine squared is 1, right? So what does the identity for sine squared theta have to be? I mean, sort of, I guess you can change cosine squared theta to what? 1 minus sine squared, right? And you can derive this. But I'll leave some of those steps to you. But you can see that that must be true. I mean, that's good. That's consistent with the Pythagorean identity, right? If I add those identities, I get a half plus cosine 2 theta divided by 2, and a half minus cosine theta divided by 2. So the cosines cancel, and you're left with a half plus a half, which is 1. It's good. What other identity do we sometimes use? How about this one? If I look at sine of theta plus theta, what do I get? Sine theta cosine theta plus sine theta cosine theta, which is what? Sine sine of 2 theta is 2 sine theta cosine theta, which is an important identity for physics. We use that to derive the range identity, for example. All right. Now, so I'm basically showing, one school of thought is if you know these adding angles formulas, you can derive almost all other trigonometric identities from them. I actually prefer a different viewpoint, which is not in your textbook. At least I haven't found it, which is known as imaginary exponentials. All right? If I have time today, I'll show you those. There's a reason that, we're about to see that there's a really interesting interplay between these sine and cosine and tangent and cotangent and what are known as hyperbolic sine, hyperbolic cosine, hyperbolic tangent. For every trigonometric function, there's a corresponding hyperbolic function, all right? So that's what we're going to talk about now. This is the next section in your book, section 7.8. And to start that discussion, I just want to draw your attention to sort of a general fact of the study of functions. If I have a function, and by the way, there should be time for some homework questions tomorrow. I have to get through a certain amount of material this week, otherwise we'll be in trouble. But there should be time for homework questions. There will be time for homework questions before I collect it, all right? If there somehow isn't time for homework questions the rest of this week, I will push the homework back to Tuesday, okay? I do want you to have time to ask homework questions in class. It's just, I blame Trump. Okay, so not entirely genuine, but okay, consistent with my comment. So, if we have, oh, by the way, is the audio bouncing on that? Okay, good, I guess that's weird. This is a simple identity you can write for a function provided that x and minus x are both in the domain, right? Like I couldn't write this if my domain was like the interval from 2 to 3. It wouldn't make sense to write this because like 2.5 would be in the domain, but minus 2.5 wouldn't. But provided my function has a domain which is symmetric about the origin, I have this identity. See what I did? I just added 0. I added and subtracted the same thing. And I said a half plus a half is 1. All right, more than that, you can easily check that the first thing is an even function, and the second thing is an odd function. So what this little identity shows to us is that any function, symmetric domain about the origin, can be written as a sum of an even and an odd function. When you apply this general idea to the exponential function, you get what are called hyperbolic sine and hyperbolic cosine. So in particular, e to the x is equal to 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. This first thing is called the hyperbolic cosine of x, or cosh x. This second thing is called the hyperbolic sine of x, or sinh x. So, properties. What are properties of sinh and cosh? First of all, you might notice that d dx of cosh x is what? By the chain rule, right? Which is what? It's sinh. So the derivative of cosh is sinh. And through almost the same calculation, the derivative of sinh is cosh. So that's like sine and cosine, but also unlike, right? There's a minus sign difference. See that? We should also notice that cosh, well, as I was just telling you, cosh of minus x is equal to cosh x, and sinh of minus x is what? Minus sinh of x. So cosh is even, sinh is odd. Something related to that is if you look at e to the minus x, what do you get? Right? Do you see that identity, why that follows? If I put in, if I replace x by minus x here, it's just cosh x, right? If I replace x by minus x, I get minus sinh x there. So it's just a simple yes, sir?
Is there any way to relate hyperbolic trig functions to just function?
There is. I'll show you that in a minute. I'm glad you asked that. You've just given me an excuse to go outside the bounds of the book. Great question. All right, so before I get to that, though, what happens if you multiply e to the x and e to the minus x? Yeah. Let's look at that. So we have e to the x times e to the minus x is equal to e to the x minus x, right, which is e to the 0, otherwise known as 1. So what that tells me is 1 is e to the x times e to the minus x, right? But that is cosh x plus sinh x, right? Times cosh x minus sinh x by the identity I just wrote over here. Let me call it Pac-Man. By Pac-Man, yes. What, you guys don't know what Pac-Man is? Am I so old? All right, let's see here. See here, 1. Not talking about the NFL or anything. All right, so cosh squared x minus sinh squared x is 1. Right? Because what I have, look at the pattern. I've got a plus b times a minus b, which is a squared minus b squared, right? The cosh sinh and the minus sinh cosh cancel. I'm left with cosh squared minus sinh squared. This is the analog of the Pythagorean identity for cosh and sinh. All right? Much later in the course, we'll see that cosine and sine parameterize circles, whereas hyperbolic sine and hyperbolic cosine parameterize hyperbolas. It's much tied to this identity I just wrote. Now, what else can we do here? What happens? So we're like, well, these are kind of similar. What would happen? What would happen if I tried to like investigate something like, you know, which one do you guys want to do? Do you want to do the? We can pick any of these to try to do. What do you want to do? Let's look at sinh times cosh. See what we get. So we get 1/4 e to the 2x minus 1 plus 1 minus e to the minus 2x. What I did there was to use the e to the x times e to the minus x is 0. Right? But you have 1 that gives you 1, and the other product of e to the x and e to the minus x gives you minus 1. Of course, those cancel, right? What is this? I mean, this is... What's that? Yeah, that's the sinh of what, though? Yeah, sinh of 2x. So there you have it. Sinh of 2x is equal to twice sinh x cos x. So this time, it's exactly, it's pretty much exactly the same identity, right, as we had for the trigonometric case. So, if there was going to be something similar, let's see here. When does this class start? 9:20. So we end at 10:10. Okay, good. All right. So there's some other basic stuff I owe you here before I get distracted by his awesome question. What does sine? What does sinh and cos look like? I mean, just look at their formulas. Cos is an exponential plus an exponential, right? And sinh is an exponential minus. Now, e to the x blows up as x goes to infinity, right? And it gets tiny as x goes to minus infinity. And vice versa for e to the minus x, right? E to the minus x blows up to infinity as you go to minus infinity. So both of these cos's and sinches, they're essentially like exponential functions if you go far out. And so long story short, cos basically looks like a big parabola, and sinh looks something like this. So the smallest cos's is 1, and sinh. So, well, I mean, I could prove this, but I'm a little bit short on time today to do that, so I'll just tell you. Cos x is greater than or equal to 1, so cos is non-negative. The derivative of sinh is cos, right? That shows you that sinh is always increasing. In fact, sinh is an example of a one-to-one function on the whole reals. It just keeps climbing. Right? In other words, sinh of 0 is 0, but that's the only thing that's 0 for sinh. It just keeps going. But the large scale behavior is basically like exponentials. Okay. So I know it looks like I've just written a quadratic, what's the word? Yeah, a quadratic graph, a parabola, I think is what they're called. And this looks like a graph of a cubic, but that's just the limits of my artistry. These are exponential tails to the left and right. Okay, so imaginary exponentials in a nutshell. So the key identity is this. I squared is minus 1. But this is actually where it gets interesting. This is called Euler's identity. E to the I theta is equal to cosine theta plus I times the sine of theta. Let me show you why that must be. So e to the minus theta, e to the minus I theta is what? So what am I using there? Let me write down one more step. This is cosine of minus theta plus I times the sine of minus theta, right? But cosine's even and sine is odd, so I get cosine theta minus I times the sine of theta. All right? Now, you'll have to trust me when I tell you that imaginary exponentials obey the usual laws of algebra. So like e to the I theta times e to the minus I theta is e to the I theta minus I theta, which is e to the 0, which is 1. But what does this mean now? This is cosine theta plus I sine theta times cosine theta minus I sine theta equal to 1, which gives us what? No, cosine squared theta minus I you added, very good. I squared sine theta equal to 1. You notice that the the plus I and the minus I sine theta cosine theta terms cancel. Just like the sinh cosh terms canceled in our last calculation. But I squared is what? Minus 1. And this is the what? The one you guys already know. Yes. Thank you, sir. That's a sine squared theta. You're like, okay, well, so, but I already know this, so what do I care, right? Yeah, okay, fine. Fine. Cynics. Let me show you how to think about something that maybe you already know. How about sine 2 theta? Let's look at, oh, that's a bad one. Let's look at cosine squared theta. Oh, I'm sorry. I've forgotten the other thing I need to do before I can do that. Related to what the gentleman did, he added. That was actually very useful. So if you take these, right? Let me just make myself some more board space. So what did you get when you added these? What did you tell me just a second ago? 2 cosine theta. See, that's pretty awesome because that means that cosine theta is 1/2 e to the I theta plus e to the minus I theta, which is a precious formula because it changes cosine to a sum of exponentials. And the laws of algebra for exponentials are easy. If we subtract, what do we get? We can derive that sine theta is 1/2 times I times e to the I theta minus e to the minus I theta. So this is how we do sine and cosine in terms of imaginary exponentials. So suppose I want to derive an identity for cosine squared theta now with this newfound insight. All I got to do is convert it to imaginary exponentials. So what I face is 1/2 e to the I theta plus e to the minus I theta. I square that. What do I get? I'll write it all out in gory detail. Right, those are the terms. When you FOIL it out, what is that? Well, yeah. What are these? 1. 1. So this is, plus 2. So what I have is I've got 1/2 of 1/2 e to the 2I theta plus e to the minus 2I theta plus 1/2. Hey, what's that? That's 1/2 of cosine of 2 theta plus 1. I don't know if you can appreciate this or not, but the way we arrived at the identity for cosine squared was direct here. Once you accept the weirdness of the imaginary exponentials, we just do an algebraic calculation to derive the trig identity. That's cool. I mean, because that means I don't have to memorize this stuff. I can just derive it if I understand this. Oh, and you can derive so much more than just this with this, as we'll see from time to time in here. As we treat harder questions of trigonometry, I will pull this tool out of my toolkit and use it. It's very, very clarifying sometimes. You're like, but I'm not comfortable with e to the I theta and e to the minus I theta. Well, I know that. That's why I'm telling you about it. All right. And I know personally I would have greatly benefited from having seen this when I was where you are, which is why I'm doing it. It's not to be mean. It's to try to help, believe it or not. Now, I still haven't answered the question he asked me, which was, can you relate cosh and sinh and sine and cosine? You see, now I can. Because what would it mean if I wrote cosh of I theta? What would that be? right? If I just plug in I theta into x, see what I get? 1/2 this. But what is that? That's cosine theta. On the other hand, if I look at, say, sinh of I theta, it's a little bit more complicated. See, what am I missing? This is almost sine theta, but something's missing. Yeah, so how do I make an I appear? Multiply both sides by I. Divide both sides by I. I will almost listen to you. I will multiply and divide by I on the same side, which is like multiplying by 1. But then this is sine theta. So yes, sine and cosine and cosh and sinh are related in this way. Now, some people would say this is just formal nonsense because you don't really understand it until you take complex analysis, and in some sense that's true. But if I want to take that kind of viewpoint, I could also criticize every function we use in here. Have you guys ever constructed real numbers? What is a real number? Do you know? Real numbers are actually really complicated things if you construct them from base principles. So I don't think it's bad to use this notation because it is stupidly useful. Anybody? Oh, I'm supposed to call names. So you can cut it off. I don't want to.